So in this video tutorial, what I want to do is walk you through a little lecture on why raster concurrency is so important in change detection. And this will be applicable to pretty much any raster algebra problems you want to deal with in ArcGIS, but particularly to our geomorphic change detection software. So we'll go through some definitions, problems with ignoring concurrency, and then we'll explain what ArcGIS does, and then why it's so hard to fix, and kind of what the crux of the problem is and how this comes about, because being aware of that's the best way to avoid it. And then we will go into what we require in the change detection software and why, and some good practice and workarounds. So just on basic terminology here, all rasters have the following primary properties. So if you were to right click on any raster layer and go under the source tab, you would see that there are columns and rows, cell size, pixel type, and also the extent. And so these are the primary properties. So the number of rows and columns, these have to be integers. And this is pretty straightforward. Cell resolution, the grid size can be, those can be floating point, decimal values, and they are in the units of whatever spatial reference you're in. So in this case, this is meters. And then the lower left coordinates, or the top, bottom, and right left coordinates, this is basically just your extents. And so if you have a number of rows and columns, you can, and the lower left coordinate, you can figure out your top, bottom, right, and left coordinates. Otherwise, here they can just be specified. And from these primary properties, the secondary properties of width and height can be derived for your raster. So there's this term called orthogonality, or orthogonal. And so for two rasters, here I've got one raster in black and one raster in red. For two of them to be orthogonal, they must share the exact same grid resolution. And so notice here that the resolutions of these grids are exactly the same. They also need to share the exact same grid centers, so they have to be aligned in both the easting and the northing. And so these are two grids that have different extents but the same grid resolution, and they are aligned perfectly. Well, I didn't draw it perfectly, but bear with me. So that is different than concurrency. So orthogonality is a more general case. Concurrency is a little bit more specific. So the grids, in this case I got a black grid and the red grid, they have to be orthogonal, so they meet the same criteria, but they also have to share the same extent. So these two grids currently, the black and the red, are not concurrent. If I were to clip them down to the intersection of these two grids, now they're concurrent because they share exactly the same top, left, right, and bottom extent coordinates. Okay. So another bit of terminology here is masked extents, which comes up in rasters where you may have some cells with no data. So if this is, say, an original raster, and then we want to put some sort of mask on this, so we want to keep the values with the magenta, get rid of the values outside that area, this is what the output mask would look like. And so the rasters that have the same mask extent simply have the same no data cells. This mask can be derived from either a polygon or a raster input. And so if you use a concurrent raster mask, that is going to be the most accurate, because if I had a polygon along here, I would have to generalize about where that boundary is, or make some sort of assumption if it's covering all of the cell or part of the cell, where do I clip that off? And if my raster that I was using as a mask raster was not concurrent, then I'm going to have some sort of interpolation problems as well. So the most accurate would be a concurrent raster mask. Okay, so those are some basic definitions. We talked about what are the main properties of a raster, the orthogonality of two rasters, the concurrency, more specific case than orthogonality, and then we also talked about the extents being common with a common mask. Okay, so the problem with ignoring some of these things, which is what most people do, is that if we ever want to do any map algebra, the rasters need to be compatible, or in other words, they need to be concurrent. The reason for this is pretty simple. Here's one example where I've got two layers here, and they've obviously got different grid resolutions and different orientations and origins, and so they are not concurrent. And so if I wanted to, say, subtract layer 1 from layer 2, how do I do that? What are the values that I use? Do I use the value here for cell A, and then what do I subtract from that in layer 2? Is it this cell, or is it this cell, or is it this cell? So there's these questions about how to go about that. Here's a case where I've got two rasters of different grid resolutions, and they're not at all orthogonal. You can see they're shifted off here. And so again, the same questions line up or come up in terms of how do I do this map algebra operation here to get myself an output. So this is obviously important in the primary thing we're concerned about here, which is change detection between two digital elevation models. That is a simple raster algebra subtraction operation where we take the on a cell-by-cell basis. If we zoom in here to our raster, here's our new DEM, here's our old DEM, and we want to go through and in each cell subtract the values in one from the values in the other and get a dem of difference in this case. And so if these things aren't concurrent, we're not going to be able to do that accurately. And so what you really need is definitely orthogonality, because if not, what cell values do you use? You've got this problem again. We want concurrency. It helps, but in fact, if some of the cells don't exist because, let's say, I've got an orthogonal grid, but that's not concurrent, that just means I'm going to have different extents, and so there's no calculation possible outside the area where these grids don't intersect. So concurrency is nice, but it's not as fundamental as orthogonality. And similarly, do all cells have to have a value, i.e. the same masked extents? Well, sort of, but most calculations will proceed and they will only do the operation, so like subtraction in this case, where all rasters have a value. So basically the intersection of cells with a value is what you end up with as your output. There are some operations like max and min functions that may still be possible even if you don't have the same masked extents, and they'll still give you an output even if only one of the inputs has a value in that cell. So this is just an illustration here of that concurrency that we were just talking about. Okay, so if I have the same number of rows and columns, so here's one raster, here's another raster. This case, I've got the same grid resolution, the same sizes, I've got the same orientation, but I've got different origins and therefore different extents on this. And another scenario I could have here is where I've got same number of rows and columns, but this time their orientation is shifted. Okay. Another scenario here, I've got the same number of rows and columns, same origin in this case, or lower left corner, but I've got a different cell resolution, and so now I've got different extents. And so these are all examples of ways in which grids are not concurrent. And so where does this matter? Well, have you ever seen something like this? This is a digital elevation model. And if we look back at this scale, it looks, it's recognizable. You can tell what's going on here. But there are these really consistent horizontal and vertical bands. Now, is that some sort of underlying geology in this area where you've got some weird, very consistent fault blocks or fault scarps along here or something? It turns out that no, that's not at all the case. Where these consistent lines are actually are systematic errors, and both the vertical and the horizontal, and they're minor enough that most people just sort of see this stuff and just kind of look the other way and don't really think about it, but they're completely unnecessary, and they come about as a result of resampling a raster to extents that were not orthogonal to the original raster. And so when that raster was resampled, there was these minor little interpolation errors that were introduced, resulting in these consistent banding patterns, and those are unnecessarily introducing errors that if we're going to do stuff like change detection, we want to do without those sorts of problems. So what does ArcGIS do, which is where most of you are going to be working? Excuse me. Arc hides the user from all this, and so if you give Arc two overlapping but non-orthogonal rasters, it just lets you do the raster algebra. It does this by combining the environment settings of whatever tools you're using to select the extents and a grid resolution, as well as doing often some sort of resampling to make concurrent grids so that the raster algebra can be done. And so the result is the geoprocessing tool usually works. This is the nice thing about ARC. It just lets you sort of sloppily go through this stuff. But the downside to this is that the user has absolutely no idea most of the time what ARC did to get that result. It just sort of appeared. And so let's look at the first of these two, the environment settings first here. And so for extents, it tends to take the intersection as the default. This tends to be the default way that it comes up with the extents it's going to use. And then for cell size, it tends to take the maximum cell size of the inputs, which makes sense. You generally don't want to subsample a raster because you don't have any data at that finer resolution, so you're not going to get anything further by subsampling it. And so every single tool, you can be in a tool and you can click on the environments and you'll bring up the environment settings, and it will then allow you to change the environment settings. There's a whole bunch of different things you can change, and I'll show you in a second the two that we're going to be most concerned about. One is output coordinates and the other one's going to be raster processing. And so one of the things that gets really confusing in ArcGIS is that there are different levels of environment settings. And so there are these application-wide, system-wide defaults that are the first guess for what environment settings get used. And so an example of environment settings here, so processing extent and raster analysis. In processing extent here, this is where I'm going to specify what the size of my raster is, its bounding coordinates, and then in raster analysis, I'm going to specify my grid resolution. And so where does that come from? Does it come from system-wide, or does it come from the individual tool that you're using, or if you're perhaps using a model or a script? These tools and models may have their own built-in settings, some of which, if you go in and customize the environment settings, you will override, and some of which don't get overridden. So it's really inconsistent across some of the tools, and sort of confusing to wrap your head around exactly which one takes priority. So let's look at the second problem here. So we said that how ARC gets away with just going ahead and doing your raster algebra anyway is by combination of environment settings and resampling. So resampling is the process by which we take, in this example up here in the upper right, a finer resolution raster, and we're going to resample it to a coarser resolution. So this is going to be our input, and we're going to do something and resample, and the output will be in this coarser resolution. So there's a tool, the resampling tool, and there's different methods by which you can resample. And so you can take your input grid, and so in this case our input grid is going to be what's represented, the cell centers, by this rotated diagonal grid. Those are your inputs. And then the output grid in this case is this finer resolution raster right here, which is rotated off of this other grid. Okay, and so if I want to figure out the value in this yellow cell at the center of that yellow cell in the red, one method is to use what's my nearest neighbor. So I look all around me, and this is my nearest neighbor, and I use that value. Another method is what's called bilinear interpolation, and in this method what I do is I look around me for the 4 closest cell centers, and then I take a weighted average based on how far away they are from me to calculate this value. Another method is cubic convolution, which works in exactly the same way, except instead of the 4 closest, it looks for the 16 closest. And so these are a couple of different resampling techniques, and different tools have different defaults, and oftentimes you don't know what they're using. Nearest tends to be the default for most tools, but it's not always the case. So that's what ArcGIS does to let you get away with murder and be really sloppy in dealing with stuff. And so what happens is you get these non-concurrent rasters, and oftentimes the examples aren't as extreme as, say, something that I may have, let's see here, shown you, like in these examples. They're often not quite as bad as this, but the examples are often very subtle, so subtle that sometimes you won't even notice. And so where these problems come from is that most people derive rasters from precise vector data sets, so points, polygons, and they use that data, especially in the case of topographic data, to derive some sort of surface that ultimately gets converted to a raster. Well, when you do that, you are using point data that has, say, some very precise locations, and these things generally are not nice, even bounding polygons. And so what Arc does is it's a little bit inconsistent also in raster geoprocessing tasks on which things it gives priority to, whether it gives priority to grid resolution or the numbers of rows and columns, or basically you could think of this as whether it's as the extents here. And so if priority is given in a particular tool to your grid resolution, so no matter what, it's going to hold the grid resolution constant, what often happens is you'll get one extra or one less row or column. And so this is a very common problem where it looks like your grids are concurrent to the eye, but when you go in and you visually inspect the properties, you realize that actually there's one less or one more row or column than you need. By contrast, some other tools give priority to the number of rows and columns, and they hold that constant, but then you end up rounding, getting these rounding errors in the grid resolution. So you may have specified a 10 centimeter grid resolution, but then you end up with a 0.9999563 or something grid resolution as a result of holding the rows and columns constant. And so let's look at a quick example of this just to sort of take it out of abstract terms. And so this is what I mean by some vector data. So here's some points that represent topo points from a survey of a channel. You can see the faint dashed lines. Those would be my left, top, right, and bottom extents. And based on wherever these points were taken, there's going to be some very precise value that defines that left coordinate. And so in this case, I've got a left coordinate of 715,469.6649,000. And so, and then on my top, similarly, I've got these things. So they're not rounded to some nice even or whole integers in this case. And so what we'll often do is we'll create a surface from this. So we'll go tin to raster. So we create a surface. We may we'll create a surface by creating a tin of this. And this is the tin that gets created. And notice that the tin has the exact same left, exact same right, the exact same extents as the input points in this case. And so what happens then is when you create a raster from that, you'll hit tin to raster, and it's just going to inherit these extents from the tin when it's creating this, unless you exert control over it in this environments tab. So let's go take a look at how we would exert control. So here's my tin underneath those points there. I want to go in and do a tin to raster operation. I grab that tin. I might specify, let's call this a junk tin here. I might give this a cell resolution, let's say, of 0.5 meters. And if I want to just go ahead and run this, I can hit OK. Oh, I had a crash here. Oh, it doesn't like that location. Okay, so we'll try that again. Alright, so now it's created me that raster, and if we go in and look at the extents of this raster, so it's got 278 by 529 rows and columns, and then the top, left, right, and bottom are exactly oops, where did our slideshow go here? They're exactly what we had. Oh, actually, in this case, it's actually rounded them a little bit. So I've got 2230 on the top. And it looks like on the top here, it's rounded that up to 26 instead of that 2230. And so there's an example of creating a raster. I didn't exert any control over those extents, and it's given me this relatively arbitrary raster value here. Now, if we wanted to redo that, I can bring up my geoprocessing results here. I can double click on this. I can rerun it, but this time what I'm going to do, I call it junk 2. And I will go to the Environments tab, and I am going to this time go into my processing extent, and I'm going to bring in same as the points here for my coordinates, but now I'm going to just change these coordinate values and specify them to something that is a little bit less arbitrary. And so I'm going to round the top up. So I'm going to go up to 4. I'm going to round the left down, so I'm going to go down to the nearest whole number. I'm going to round the right up, so go to 9, and I'll round the bottom down. And so now I've got a raster extent that has got these nice even numbers, and recall that my cell resolution here is 0.5. And so what's critical about doing it this way is that I can run this raster here. I get this junk 2. I think you're pretty hard pressed to tell that there's much of any difference between junk 1 and junk 2. I can zoom in here to a particular area, and you can see that there are some subtle differences here in how these got created, because they do have these slightly different extents. But they were both derived from the original tin. They're both equally valid rasters. But when I want to do some later raster algebra or other geoprocessing tasks, this junk 2 now has these has slightly different number of columns and rows, 280 and 532 versus 278 and 529. Okay. But the key thing is that the extents are nice, even whole numbers, and therefore the width between the left and the right and the height between the top and the bottom are both evenly divisible by the cell size or grid resolution. And so that, it turns out, is a really, really helpful and important thing. So, back to our software, the geomorphic change detection software. What does it require and why? Well, we require concurrent grids to do the change detection because we don't want to introduce further unnecessary uncertainties by having these slight little interpolation errors that will come up if we don't have concurrent grids. And so in the beta versions, which aren't officially released right now, of GCD5, but if you ask, we can give those to you. There are, where this gets enforced is actually not at the survey library. So in the geomorphic change detection software, you build the project, and you go into the survey library, and you add in your surveys. And at this point, there's no check when you're adding those surveys in the survey library as to whether or not they're orthogonal or concurrent. What happens instead is it's enforced at the change detection panel stage, where if you try to load a new and an old survey that are not concurrent, you'll get an error message. Okay. So the reason we do this is we don't want to get, like I said, those further interpolation errors from resampling, often that the user is unaware of. Another reason is the underlying code that we use is set up, and it assumes that the rasters are concurrent. So we don't do anything fancy in terms of resampling because we don't want to. We don't use ARC's geoprocessing in the background, which often does a lot of this for us and gets us in trouble. In the future versions, we're going to, well, sort of pull an Esri and shield the user a little bit from some of this, but not entirely. What's going to happen is when you load a raster into the survey library, we're going to we'll make a copy of it, and we're going to, at that stage, we're going to enforce orthogonality. And so all rasters that get loaded will have to be orthogonal to each other. And then we're only going to check for concurrency and enforce it at the time of change detection. So when you want to compare two surfaces, what we will do is take the intersection of those two surfaces and derive a concurrent raster, which is very easy once the grids are all orthogonal, and then your outputs will be then taken care of, and that should work a lot better for folks. Right now, people have been having lots and lots of issues with just how do I create concurrent rasters because GCD4, GCD5, and then the old DoD3 all require it. Okay. So what can you do if you're in that boat? What's some good practice and workarounds? Well, I would suggest that you always use even's actually the wrong word, but nice rounded integers, whole numbers wherever possible for the extents to simplify your orthogonality problems. There's very rare instances where you actually need to have a raster that has extents with such, arbitrary and very precise coordinates like we saw in that previous example. I would suggest that you never use cell resolutions that are not evenly divisible into the width or height of a raster. That is absolutely fundamental, because that usually what happens is if you don't do that, everything's fine for a while, but then later on problems arise, and it's really a pain to try and troubleshoot if you haven't done that. So always exert explicit control over your extents and grid resolution when you're creating rasters from tins or terrains. So in that first example that I was showing you, going from the tin to a raster, we just used whatever the defaults were without paying any attention, and it didn't even give us what we were expecting. It gave us something close to what we were expecting, but a little bit different. God knows how it came up with that. So it's better to instead, like we did in the second example, go in and exert explicit control and round those extents up and down. Then once you get that raster defined, use that in the environment settings for every other raster you use or you derive. Every other raster, you're just going to go in the environment settings, go to processing extent, and then make it the same as this one master raster that you've ended up using. Avoid resampling if at all possible, because it's just a way of potentially introducing errors. And if you must resample, be really careful not to introduce the systematic interpolation errors. And so, like I say on this last page, the best thing to do is exert explicit control over the cell size selection and raster extents at the stage of raster creation, but to ensure that raster width and height are evenly divisible by cell size. But this is not always possible, right? So this is the best thing, but oftentimes all you have are the rasters to work with. And so I'm going to walk you through two quick-ish examples here on some common problems. One is where I have two non-concurrent DEMs and what I do to make them concurrent. And I unfortunately don't have the raw data to produce tins or terrains, and I don't have the original tins to create some nice concurrent grids from. And then the other one is where it looks like I've got two concurrent grids, and they actually are, but because of the way they were derived, there's slight rounding errors, and when I get to certain tools, I end up having trouble. Okay, so let's go into ARC, and let's deal with this simpler one first. So what I've got here is two LiDAR DEMs that a user sent us from a stretch of river here. If you zoom in, you can see them here, 2006, 2008, and so someone wants to do some change detection on this, okay? And that's perfectly reasonable, but if I go into my original LiDAR DEM, I've got 12,088 and 7,830 for columns and rows. I go into this other one, and I've got, instead of 12,088, I got 13,220 and 8563. So clearly these things are not concurrent. Are they orthogonal? Well, cell size in this one is 0.914. Cell size in this one is 1 meter. So no. So this is a problem. And then also, if I look at my top, left, right, and bottom, these things, the extents here, are going to be completely different as well. So how do I get these two grids to be concurrent? Well, there's a bunch of different ways to do it. I'm going to show you one. And I'm going to make my first surface here. And I'm going to just use the raster calculator to do it. And I'm going to take my original 2008 DEM. And I'm just going to double click on this. And then what I'm going to do is I'm going to use my environment settings. And I'll go ahead and put this in here. And I'll call this okay. Okay. And I'll use my environment settings to control my processing extent. And so what I'll use to start with here is the original DEM. And I'm going to just round this one down. I'm going to round that one up. I'm going to round this one up. And I'm going to round this one down. Okay? And then I'm going to go to raster analysis, and instead of just doing maximum inputs, I am going to make sure that this is a 1 meter resolution raster. Sure it is, right? And so I will run this. And what we would expect as an output is something with the extents that we specified and with the cell resolution, and those extents will be different than the original. We can see how this is doing here. Okay, so notice that my new raster here, it's a different color ramp, obviously, when these come in, but here's my new raster. Has a very similar elevation range, exactly the same elevation range, but this has been resampled slightly to correct for to give us a better baseline raster from which to establish concurrency. So let's look at the properties. So 1 meter and 1 meter. There's our number of rows and columns, and then let's see, and there's our rounded extents. And so what we'll do now is we'll run raster calculator again, but this time we'll run it for the 2006, and I'm going to go into environments, and because I double clicked on that in the results tab, it brings up the exact same environment settings as we had before. Alternatively, I could say make it the same as my concurrent DEM. That's going to be exactly the same. Okay, there's a couple different ways to go about that. But I can run this one now. And while this is running, I'll just remind you that a better thing to do would have been to go back to the raw point data or the tin or terrain surface and derive the raster from there, because what I'm doing here is I'm taking a raster in this instance that has a 0.914 cell size, and I'm bumping it up to a 1 meter cell size. So to do that, I obviously have to use one of these methods. And I think what raster calculator is doing is nearest neighbor, but the ArcGIS documentation is actually pretty weak and doesn't tell you what a raster calculator does. So it's better to actually go back to those raw ones. So here's our 2006. So 1289, 7831. 1289, 7831. So now I've got two concurrent rasters with nice rounded extents, and they are ready to go for use in the change detection software. So that is one example. The other example that I wanted to share with you was an example where the DEMs do appear to be concurrent, but we have problems. And so I will show you those two DEMs. So here's a 2010 survey. There's a 2009 underneath of it. And so you can see that those are different when I swipe that 2010 back. And if I want to check these for concurrency, I go in, I look at this. It says 970, 1570, 0.1, 0.1. That's okay. And then I look down here. Notice, whoops, those are statistics. Oh, I've got myself confused here. I apologize. So here are the two original DEMs that appeared to be concurrent. So I go to the properties of this. 963 and 1558, 0.1 and 0.1. Okay, so remember that. 963, 1558. Go into here, 963, 1558, 0.1, 0.1. Go down to my extents and notice that I've got these sort of arbitrarily precise non-rounded extents. Okay, so if I come in, I've already loaded these into my survey library. So here are these two that I just showed you, and then these are the two that I've adjusted. And if I was to look at one of these, notice this. Now, in the previous properties, in here, in the arc properties, it showed us that it was 0.1. Well, it rounds it up for display purposes. But this is actually the number that's stored in the cell size resolution, which is not 0.1. And the reason for that is because 0.1 is not evenly divisible into the width and the height of this. There's this minor rounding error here. And so if I look at that one and I look at this one, they both have exactly the same issues with the extent and the cell size. They're exactly the same, so they actually are concurrent. But I'll show you a place where this gets us in trouble. So I can go in, because those are concurrent, and I can go with my old and my old, and I'll just do a simple change detection here. And I can calculate that change detection. Let's see here. Not sure why that didn't show up. But I'm going to save it anyway here. Simple DOD, old we'll call it. Okay, so there is a simple DOD. And this thing got produced, but there were just no issues because those were concurrent grids. But now what happens is I go to budget segregation, and I'm going to use that simple DOD old, and then I want to segregate this budget. I want to segregate it spatially. So I'm going to use, I've got these polygons here which classify the extent of difference in some way, and I want to know what are the change. What I've got here is this. I've got a field called geomorph. I'll add all the values from it. Okay, and so I want to know in these different colored areas, for example, how much channel incision is there versus how much pool scour, how much questionable change, etc., etc. So the way I do that is with budget segregation. I select that DOD that I calculated. I load up a mask. I've got to remember where I put this clutter. No. There it is. Load up a mask. I select that geomorph field, and I hit calculate, and now I'm going to get an error. So, details of that error. Input layers are not concurrent. That's the error we get. Now, if I close this out, it's pretty clear that the input layers were concurrent. But let's see what was happening in the background here. Go in here. What happened was this used the polygon to raster function. And it actually created a polygon to raster successfully. You can see that it did that here because this thing doesn't have a red X on it. I'm going to add that to the display. So now this is a raster version of that mask. That's what it needed to do in the background in order to do that budget segregation. Now, the problem is, I go to the properties of this, 964, 1558, 963, 1558. So that little minor, you wouldn't even see it in these properties here. You see it in the rows and columns, but what happened was it was obviously preserving that 0.099999 cell size, but at the expense of the columns and rows. And so it ended up having to add another column onto there, and therefore this seg35, this temporary raster that gets produced in the background that you don't even know about, was not concurrent with the DOD right here that we were trying to mask it from. So that's 963, 558. This is 964, 1558. And that, therefore, is where we get that error message. So the workaround to that is to create some concurrent rasters. And I'll just show you in the survey library. And I've got these two concurrent rasters here. But this time, notice I've got even, or rather rounded extents here. Rounded up to the nearest whole number on the extents. And so both of these have the same extents. And so if I have, which I do, some change detection examples which were done from those. So here's one, and I load up that mask again, and then I run that geomorph again on it for the budget segregation. This hopefully should work, and there it has. And so now I've got all these categories working as I would expect them to. And the reason for this, we will see when we go into the results. There's another polygon to raster that was done again. If I add this one to the display, it looks exactly the same, but this time, because I had evenly divisible width and height by the grid resolution, this 970, 1570, exactly the same as my inputs, and so I didn't get that problem. So that's quite a bit to digest there in 50 minutes, but unfortunately I've had so many people with problems on this. The only way I really knew how to lay it out was to really cover the basics and then go through some explicit examples. And so hopefully what you take away from this is that you really do need to care about grid concurrency, orthogonality, etc. And the good practice for the fixes for this are actually pretty simple. You just need to be conscious of them and very consistent with them up front. And after that, everything's easier. The newest version of GCD5, when we release it, will hide a little bit of this from folks, or at least prompt you to fix some of these things. But it'll help you with them. But for those of you that have been struggling getting some of the older versions to work and the beta releases to work, hopefully this helps. Best of luck.